We are ready to use the chain rule with Leibniz notation. For the sake of time here, I am going to omit the proof of the chain rule. It does involve a couple of difference quotients that are composed. It's better to be spending our time to analyze the relay of information just from the composition of functions that you learn in algebra. The key is to be able to identify the inside function, which is u of x in this case, versus the outside function, which is actually g of x in this case. Keep in mind that x here is not the same x for g. In fact, if you read this carefully, notice if you're given y as a composition of functions, g composed with u of x, if u is differentiable at x, and g is differentiable at u of x, then we could write the chain rule, which is actually the product of two rates. Let me repeat this one more time. Notice x is in the domain of u, and once you take the output, u of x becomes part of the domain for g. So that's why it's very important to read the inside function first. U must take place first, and then g must take place second. There are two ways to read this notation of the chain rule. One of them is the derivative of y with respect to x is equal to the derivative g with respect to u times the derivative of u with respect to x. Another way of reading the exact same notation is actually the derivative of the composition is the derivative of the outside function evaluated at the inside function times the derivative of the inside function. Now, this second way of reading the chain rule matches much better with prime notation. The derivative of the composition is the derivative of the outside function evaluated at the inside function times the derivative of the inside function. We'll begin by mastering Leibniz notation first, and then over time, you could also evaluate the chain rule using prime notation. Leibniz notation is very important. It's very important as we are going to use it for implicit differentiation. And implicit differentiation is going to be very important as we're going to need that to study related instantaneous rates of change. So all these are going to go hand in hand. We need the chain rule in Leibniz notation, then we need implicit differentiation, and then we need instantaneous rates of change. Rates of change, meaning they are plural, and they'll use both the chain rule and implicit differentiation. So I'm going to illustrate some examples here on how to use the chain rule. At first, you might need to spell out some details. You might want to make an aside column just so that you're able to identify the inside function and take its respective derivatives. So let's look at the inside here. And then the outside function would be g. And remember, the chain rule says to do this. If y of x is composed of g composed with u of x, then the derivative of y with respect to x is equal to the product of two rates. Derivative g with respect to u times the derivative of u with respect to x. No problem. Ready to differentiate this? And notice once you have memorized the chain rule, once you're able to identify the compositions, you're simply going to make a substitution. Now you're probably wondering, where is g of u? It's actually right here. Instead of calling g of x is equal to the square root of x, we could actually just call this g of u. Is the square root of u. And this will now be a little bit easier to understand. Now this is almost done. We need the derivative of the outside function evaluated at the inside function. So the inside function was 4 plus 3x to the 17th power times the derivative of the inside function, which we have 51x to the 16th. And if you multiply those two together, you could actually simplify and get an answer. I'm going to go ahead and conclude with function notation or prime notation. Now, if you look at this carefully, the previous step is the key. This is the derivative of the outside function evaluated at the inside function. Multiply by the what? By the derivative of the inside function. And so notice it does match this saying right here. Whether you use Leibniz notation or prime notation, you will be able to spot that saying during your computation. When you simplify it, though, you will lose the pattern. So make sure you're able to show your work up to the extent where you could see the product of two derivatives and they're multiplied together right there. Some of you might be able to spot the outside function first. You know, different people see different things. Notice you're now just going to substitute. So that is the derivative of the outside function evaluated at the inside function. Now I got to multiply by the derivative of the inside function, which is that. We're going to go ahead and finish this with prime notation. Just a few more examples here. You might want to take this opportunity to pause the video and try these problems yourself, and then you could unpause the video later and see if you could check your answers. See if you could check your writing to match with mine. Notice that for all these examples, we're starting with Leibniz notation so that you don't lose this notation. This notation is especially important in sciences like physics, biology, and chemistry, where variables are always changing and they line up with the storytelling of Leibniz notation. This example here requires a trig identity, so that's why your simplification and your final answer looks so compact, and that is because trigonometry is a language. Just more examples here. Once again, feel free to unpause the video to check your answers, and make sure you pause the video to try these on your own. Keep in mind when you're writing Leibniz notation, make sure you're able to read this out loud. You're trying to say the derivative of f with respect to t is the product of two rates or the product of two derivatives. As long as it is the chain rule here, you'll see that it is the product of two derivatives. It's the derivative of the outside function evaluated at the inside function. Times the derivative of the inside function. And then finally, use algebra to simplify. Remember to conclude your function, your new function, with prime notation. That way you are mastering both notations. You know how to read both of them, and that you'll be ready for implicit differentiation and related rates of change with Leibniz notation. So that is saying the derivative f with respect to theta. Make sure you practice saying that out loud, and you recognize that theta is your independent variable and your dependent variable is f, or f of theta. This example here, you do have to be careful. You're going to use the product rule here. So when you look at this, pay close attention that you're using the product rule. And inside that product rule, you're going to go ahead and use the chain rule. Once you realize that you're doing that, you're going to go ahead and simplify your answer by factoring out the greatest common factor.